So let's look at how we're going to define a positional change mathematically. So this in effect is a positional change for any particular function. So let's start off with the idea of a straight line. So if you get a straight line here and you can work out the gradient of that line, it's going to be the rise divided by the run, which is your delta y divided by delta x. So that will give you the gradient of this line. So we could write that m is equal to delta y upon delta x. So hopefully there's nothing new in that for you. We could rewrite this in terms of delta y, and we could say delta y would equal the value of m delta x. So we're saying that this height here is equal to the rate of change at this point times this distance. So the height here is the rate times the distance. So again, nothing new in that. Now if we were to do the same thing, but except now that we don't have a line, we actually have a curve, then again we could take that same point and we could draw out our delta x and delta y. Now please note here that these values here, delta x and delta y, they're not infinitesimal values, they're just small values, which are different things, okay? So if we were to look at the value delta y here, then we could say that the value of our delta y is equal to the rate of change of the function at this point times our delta x. So the rate of change of the function here at this point is our df by dx. So that just gives you the gradient of the function. So df by dx times delta x is equal to our value of delta y. Now note again, as I mentioned here, that these distances here aren't infinitesimal distances, so they're actually fixed distances. So this here would give us a height here, which wouldn't be the actual new next point on this graph, it would be out by a certain amount. So now we could equally write it in a different format. We could replace the x's with the y's and the y's with our x's. So we could write that as df by dy times delta y would equal delta x. So there's nothing new in that, we're just simply changing the y's for x's. So if we think about the idea of our hanging rope, we've seen that the potential energy is given by this functional here, and we chose a particular value for y of x which will minimise it. But we're not actually interested in the integral from 0 to L here. All we're looking at is one infinitesimal little section of this rope. We're not looking at the rope in its entirety. So we could go ahead and we could take this section off. So we get rid of the integral sign here and we're just left with this little part of our function here. So this is our function f here, and if we were looking at changing that or finding what happens to the potential energy as we change the position, then what we would do is we could differentiate this function here with respect to y, and we would be holding x constant. So we'd be holding x constant, therefore it would have to be partial f by partial y, where x is a constant, and then if we were to multiply that by some distance delta y, then we would get the change in the potential energy. Now we're not doing it for a hanging rope, we're just trying to do it for any general system. So the function f here stands for, in this instance here, any particular function of this form. So we can say then that our partial f by partial y, where x is held constant times delta y, would give us a change in this value, and we'll just call the value, rather than call it potential energy, it's a general value, we'll just call it S1. So that'll give us a change delta S1. So really this is what we've been looking for. We're looking for a mathematical equation that tells us the change in our value whenever we change our position, and this is the equation that we're looking for here. So that's all for this video. In the next video we'll go and we'll look at doing the same thing, but we'll look at for a gradient change. Goodbye.